back to EC TechNest. In this lecture, we'll be discussing about the sharpening spatial filter. The main objective of sharpening is to define the highlight and the fine details that are present in an image, and also to highlight the intensity transition either from 0 to 1 or 1 to 0, and also to enhance the details that has been blurred. So the next one is the image blurring is accomplished in the spatial domain by pixel averaging in the neighborhood, in which you are making the pixel to reach a certain average value according to the pixel values of the neighborhood elements. Then sharpening could be accomplished by spatial differentiation. Reverse operations of smoothing spatial filter is performed. Then you need to highlight the fine details present in the image. Also, you have to enhance the details in the image that is being blurred, and it is also used to enhance the edges of the object that is present in an image. Applications of sharpening would be electronic printing, medical imaging, industrial inspection, autonomous guidance in military system, and spatial differentiation can be performed by using two derivatives, first order derivative and second order derivative. So now we'll discuss about first order derivative. In first order derivative, we are considering the 1D function and plotting intensity along with the 6 discrete intensity levels. We are interested in only 3 different intensity levels, that is constant, int and ramp, as well as the step. So these are the pixels having constant intensity values, and these are the intensity transition. Next we'll look into the graph plot of how the first order derivative occurs. For the 1D function plot, a scan line of first and second order derivative is drawn, and we'll see only the intensity of the first pixel. So this is the illustration of first and second order derivative of 1D digital function. And so here you can see this is constant intensity, and here we have ramp function, then followed by again constant intensity and then step function. So this is the intensity transition point in which the function is converted from constant intensity to ramp, and here the highest intensity is 6. So first you have to write the scan line. Scan line would mean the points where we have marked in this graph. You have to write those, that point is called scan line points. So here it's all constant, therefore it is 4, 6, and here it's in 0.5, here it's in 4, here it's in 3, 2 and 1, and here we will not write 0 because it's constant at position 1. So here you will write 5, 1. Here you will write 6 ones, that is 1, 2, 3, 4, 5, 6 ones, and then after that the next point is again at 6, and you don't have any points here. That's why the scan line will continue to be 6 for the other 5 points. After which, so you have to find the first and second derivative. To find the first and second derivative, you have to consider the first term. After considering the first term, you shouldn't consider anything for the first derivative, that is it is 0 here. Then you have to subtract the second term from the first, second term minus the first term, that is 6 minus 6, 0, 6 minus 6, 0, 6 minus 6, 0. You have to write like this: 6 minus 6, 0, 6 minus 6, 0, and 5 minus 6 is minus 1, 4 minus 5 is minus 1, 3 minus 4 is minus 1. Similarly, you have to write the value. 6 minus 1 is 5, and for second derivative, you have to consider the scan line to be the first derivative line, and then you have to subtract one from another. You'll write the same 0 here, 0 minus 0, 0, minus 1 minus 0, minus 1, and continue. So this is the second order derivative. So here the points represented in dot represents the first derivative, and the boxes or the rectangles that are represented here represents the second derivative. So now the first derivative function is represented by dou f divided by dou x equal to f of x plus 1 minus f of x. F of x plus 1 is the next intensity, whereas f of x is the current intensity. So using the derivative plot, the first order derivative values for the 1D function is considered. Now applying first order derivative for the 1D function, we'll obtain the 2D function or the second order derivative. The first order derivative, the result is 0 for constant intensity, and along the entire ramp the first order derivative results with non-zero. You can see here, when the derivative is for the ramp, we have values for first order derivative, but for constant values we don't have values here. Next, we'll discuss about the second order derivative. Second order derivative for 1D function is represented by differentiating the first order derivative, that is dou square f divided by dou x square is equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. So the second order derivative, the result is 0 for constant intensity, and it is mainly used to sharpen the image. For constant slope ramp, second order derivative must be 0. Therefore, these two derivatives are used to sharpen the image. Next is, at the transition, image has been enhanced, and however, to develop the Laplacian mask using second order for the 2D image, we'll be using the Laplacian mask, and we need to rotate the image and apply the mask, or vice versa. Both the results will have the same value now. So consider the isotropic 2D image, and we'll now discuss how to develop a Laplacian mask using the Laplacian formulas. So the second order derivative for 2D function f of x comma y is given by the Laplacian mask function. So this is the Laplacian mask function, that is delta square f is equal to dou square f divided by dou x square plus dou square f divided by dou y square. So this is one equation. Now you have to write individual equations, that is dou square f by dou x square. This is the second order equation of 1D, that is f of x plus 1 comma y plus f of x minus 1 comma y minus 2 f of x comma y. Similarly, in the y direction, you'll keep the x value to be constant, and you'll replace y with y plus 1, y minus 1 and y. When we perform addition, that is addition of these two terms, that is addition of dou square f by dou x square equation along with dou square f by dou y square equation, we'll get the following equation, that is f of x plus 1 comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus f of x comma y minus 1 along with 4 minus 4 of f of x comma y. Minus 4 is obtained by considering minus 2 plus minus 2. It becomes minus 4. So this equation is implemented using the filter mask and also gives an isotropic result for increments of 90 degree. So discrete Laplacian formation is formed. So this is how you represent the filter mask. Filter mask is represented by g of x comma y is equal to f of x comma y plus c into delta square of f of x comma y, where c represents the constant in the Laplacian filter and c value can be 1 or minus 1. So you have to remember this filter mask matrix 0 1 0. It is very easy to remember. The main objective is, whenever you add all the values and subtract it with the middle value, your answer should be 0. So the border elements will be 0 and the middle elements will be 1. We'll discuss about this in the next lecture. Thank you.